cultural discussion also, part of the cultural discussion. Well, EIC will be in the US, so we all have to embrace donuts and delicious coffee. No, coffee is good. I'm not complaining. Okay, so we are shifting today from the historic sort of overview of exploration of the proton and nuclear structure towards what really EIC will bring us. So we go from, the state-of-the-art measurements with unpolarized proton-electron collisions in experiments like HERA into experiments at colliders like HERA to something, more sophisticated. And I will tell you what EIC will add to the picture and, what open questions we currently have. So the first part is sort of a continuation of yesterday's discussion about open questions that EIC will address. So I started the lecture yesterday by saying that, that the human curiosity somehow tries to go deeper and deeper into the structure of matter and understand image and understand, what's really inside. And those insights, especially into three-dimensional structure, can bring deeper understanding on the underlying theory that describes whatever we are testing, the visible ordinary matter in case of, our principles of physics and nuclear and particle physics investigation. So to summarize really in one sentence, what is the EIC physics quest? When you think about polarization, knowledge we have about, gluons, what really sits deep inside the proton, EIC will uncover the structures of proton that are currently hidden for us, especially in 3D. It will extend the reach to nuclei. We'll start really thinking about the fundamental structure of sort of nuclear matter, called nuclear matter, in terms of quarks and gluons, also taking into account spin in some cases of lighter nuclei, and will offer really a precision. So we are shifting, from first exploratory measurements to the real precision measurement of the fundamental matter that builds, me, you, and our whole visible world. So of course, EIC focuses mostly on the gluon region. We are reaching higher energy, we'll have a very wide kinematic range. So I will try to, give you an overview of the main high-level physics questions that EIC tries to answer and why really EIC came to, an idea and will come to existence. And then we will try to break down a sort of study case of measuring and accessing proton spin. This we also already touched yesterday, and this is one of the very first question about the emergent phenomena. So how the messy dynamic structure of the proton results in spin that is such a fundamental property of every particle, fundamental particle and more complex particle systems, that really when you think about it in the more high level global way, it really governs the property of matter that builds all of us, that our world is made of, right? The fact that we have fermions and bosons, the fact that matter is stable, all of those kind of originate from this microscopic property of particles they are building it. So as a summary of the previous lecture, we've seen that after decades of experiments, we've seen that quark spins contribute roughly to about 30% of the proton spin. So now the question is, and now we know also that quarks, gluons, and their motion should contribute because we have much better picture of what's inside the proton. But, the full picture of what in how much really remains elusive, especially if you are starting, thinking about the orbital momentum, about the gluons, and about more three-dimensional structure of the protons itself. So I promised you yesterday a summary of where we are right now with the proton spin, also in the region that you usually don't talk about. So we do some integral over x. We are saying that, with whatever uncertainties we currently have, the spin of the proton or spin of the quark should contribute that and then match. We show the helicity distributions flavor separated as a function of x of the momentum fractions in the infinite momentum frame. But, we kind of don't talk about some regions that we simply don't have access whatsoever so far because we don't have any data, polarized data, that is accessing those. So this is like a very, rough summary showing from one of the global fits the current work data. So what we have on those two plots, on this plot, I have this where it will get there. It also doesn't work. This works. Okay. Very vaguely. We'll get there. Oh, here we are. Okay. So on the x-axis, or maybe on the y-axis first. So on the y-axis, you have a currently known contribution from gluons and quarks. Gluons and quarks spins with very low momentum fractions, so below 10 to -3. So, current experimental data, if you are talking about, for example, proton-proton measurements in facilities like RIC with polarized, longitudinally polarized two proton beams, are roughly sensitive up to, 0.0, maybe 1 in in like direct data points. Some feeds allow us to extrapolate a bit. So in this region close to our data points, we are quite sure about what we have there. But if you start going lower and lower and lower, you see that basically the result is 0 with the huge uncertainty of the order of 300%. Of the total proton spin, right? So proton spin is 1/2, so it's like 300 up and down. And we can do the similar exercise when we are looking into how much room do we have left from the potential contributions from the proton and to the proton spin from the gluons and quarks, from the motion of gluons and quarks, right? So from the angular momentum. So once again, we know that the spin of the proton is 1/2. So then, we know how much we can extract from quarks right now, how much we have from gluons. We sum everything together and say, okay, how much is still missing from the angular momentum in, low, but in the low, from the low region, but also not, dramatically low. So 10 to -3. So you can see that, the answer is basically now 0, also with the large uncertainties, roughly, 100% of the total proton spin. So this is the current status. I mean, we learned a lot. I don't want to give the impression we didn't learn a lot. We learned, but, there are those open gaps, and really going deeper and deeper is to understand the full picture of the proton spin. But EIC, it's not only about the proton spin. Thanks to the fact that we will have very high luminosities, as well as very extended detector setups, as we learned yesterday from Thomas, it will allow us to measure particles not only in the central part of the collisions, but also very forward and very backward. Basically, the detector setups that try to measure as much as possible. I don't want to say everything, but as much as possible. We will also be able to access questions about another emergent phenomena related, for example, for the protons and neutron masses. So, often in this kind of conversation, the example is, okay, but, think about the mass of the proton. We know that inside the proton, we have quarks and gluons. Gluons are massless, quarks are practically massless. So where the all mass is coming from? And in this kind of, simple demonstration, you can say, yeah, think about how dynamic the proton is. So basically the mass that is inside should arise from its dynamics, from the energy of the constituents. So when you think about it, it's kind of mind-blowing because basically our mass, mass is probably better understood in everyday life. And when I speak to high school students or people in everyday life, when they think about mass, it's just isn't it mind-blowing that basically our mass, the macroscopic property, just arises from those flickering quarks and gluons inside the proton? I mean, it is mind-blowing. We of course want to describe it in a quantitative way and would like to link the spatial distributions of quarks and gluons, especially gluons, because we know the dynamics of these gluons is responsible for the mass, to the mass radius of the proton, and really going deeper and deeper into mass structure. And those measurements will be the measurements that will be mostly sensitive to those kind of effects are measurement of the special type of the exclusive processes. By exclusive in measurement, we mean that we try to measure every single particle. So, and it means that proton usually doesn't break. And some other particle, like for example, a photon or a meson, is being produced that directly tells us about or is sensitive to the part of the proton and a properties that we are trying to probe. So what EIC will provide is basically a first ever 3D image of gluons inside the protons. To answer the question one more time, how gluon interactions contribute to the proton mass, and how they mediate the forces that bind quarks together. And I also see it as a kind of nice analogy to the old discussion we had about 3D structure of DNA, right? So in analogy, somehow the way the double helix structure of DNA unraveled the organization of genetic information and a deeper understanding of what governs it. We think and we hope that the same, will happen with gluons. So this is an example of the distributions in the transverse plane. So this is the position distribution of the gluons that we of course don't know, but we can estimate what errors we will have on it from the expected luminosity and expected precision and coverage of our detectors. And it's one of those examples showing that that we'll try to map it over the large range of the momentum fractions carried by the gluon. So kind of zooming from a picture of the proton in the space, in the position space, where the things look like free quarks, to really gluon rich environment. It's not only about the 3D structure of the proton in position space. As many of you probably know, EIC would also unravel the 3D structure, especially spin correlated 3D structure of the proton in the momentum space. So these are some of the remarkable examples of the predictions of how the quarks like U and D are correlated within the proton with the spin in the transverse position along the momentum axis. And if you think about the current data and all the measurements that are happening in so-called TMDs, transverse momentum dependent particle distribution functions, we basically do not have data on the gluon contributions and C-quark contributions to those three-dimensional structures. So this is basically unraveled nowadays, and we will really be able to go deeper and deeper and see it in the EIC. But it's not only about this, you know, the EIC is called Electron-Ion Collider, and one can ask, okay, we are all talking about atoms and protons and neutrons, etc., but, you know, we are made out of heavier nuclei, not just protons. And I hinted already yesterday that there has been already some puzzles in understanding how really the proton and internal structure of the proton behave when it's inside a nucleus. So I like to, see it this way that, in 1980s, we've seen a proton as a very simple system of free quarks connected by gluons. In 2020s, we have a bit better picture, still, in the region rather dominated by quarks. And then, in the future, one way we will be, testing it deeper and deeper will be to understanding the contribution from gluons. And the other way will be really looking into the proton inside the nucleus. And here there, another set of open questions regarding how those densities really affect the behavior of quarks and gluons, but also looking into maybe possible state of gluonic matter, into going in the very high gluon densities. As we looked yesterday into the examples of the particle distribution functions, the deeper you go into the proton, the higher Q square you are reaching, the lower X, the lower momentum fractions you see, the environment is dominated by the gluons. So you can kind of imagine it intuitively that if the number of gluons is growing and growing and growing, like on a rock concert in a very tight room, at some point there is no more space for movement, and everyone is stuck and kind of behaves as a well-organized entity full of gluons. So the question is, when does it happen in X? And also how to really reach this state. And here, one more time, we are getting a bit help from the fact that we will be colliding electrons with heavier nuclei, because this kind of enhances the overall reach to the matter that and the region of the structure of the proton that is dominated most possibly probably by so-called gluon saturation, which you probably heard about. It's just very high level sort of introduction. And really heavy ion beams in EIC are key to create those like extreme conditions of very dense gluonic matter. Okay, so this was a sort of very high level introduction. Right now, let's see how experimentally we will be able to access the EIC physics. We mentioned yesterday deep inelastic scattering, and I called everything kind of deep inelastic scattering. But of course, we have several sub-processes or different types of processes that we will observe in EIC that give us access to its physics. So we talked DIS. What I meant yesterday mostly was neutral current DIS, when you have an exchange of virtual photon or Z particle at higher energies. We can also have access to a structure of the proton through a charged current DIS when the W is being exchanged. But then, as you can see experimentally, what is being produced is a neutrino. And as you might know, detecting neutrinos are basically impossible in our detector systems. So there are lots of DIS kinematics will rely on this X, so the final hadronic state that basically also constrains our overall kinematic system, and we can extract Q square and X, some momentum fractions also from it. we can ignore everything what's being produced here, but we can also look into the hadrons that are being produced from a struck quark, if we can sort of see it in the leading order picture. And this gives us sensitivity to what type of quark we are probing with our virtual photon. And this process is called semi-inclusive deep inelastic scattering, in which we are detecting at least one hadron or two, or a jet of hadrons, for example. And this I already mentioned in the context of space imaging of gluons inside the proton. And these are the whole set of deep exclusive processes. Deep because, of course, we are penetrating proton, exclusive because we are measuring all these particles. And this really requires all particles being detected, but also high luminosities. So here you can see, the topics coming from left to right to, what extent all those processes contribute to the overall picture of the proton. I mean, they all contribute in one or the other way, and are kind of intertwined into getting access to the 3D structure in momentum and space, as well as, I of course show here proton, but all of those can happen also on a nucleus. Okay, so now we will do some case study about how we can access the proton spin. I mean, there's so many measurements we can do in the EIC, and it's just, so exciting to choose something. But I think that proton spin is a good example because it involves lots of aspects of what the detector will have to do and how the analysis will look like. So, like yesterday we talked, okay, some cross sections has been measured. We show them as a function of, momentum fractions or Q squared. Here we are, the experimental uncertainties, we fit it to some known predictions, we are done. But of course, we all know that it's much, much more than that. It's a full process involving figuring out how we can get sensitivity to the particular process, then understanding how we really measure those, building detectors that will allow us to do so, then doing the whole statistical, data analysis, and then in the end, including it into the global fits and, understanding what we can extract out of it. So we will go somehow through all this chain. So yesterday there was a question about the orbital angular momentum. I also mentioned the composition of the proton spin. So there's the one example how we can do it to answer, more formally the question, how does the spin of the nucleon originate from its quark, antiquark, and gluon constituents and their dynamics? So here you can see the Jeffy-Manohar sum rule that was also mentioned in the 3D structure class. And you can see, roughly speaking, what we can access by what. So the quark helicity and gluon helicity can be accessed by the deep inelastic scattering or semi-inclusive DIS. There are also components from the hadron-hadron processes that I roughly mentioned yesterday in the current status of where we are. And, insight to the orbital angular momentum can be obtained from more exclusive processes like the deeply virtual Compton scattering or meson production. Okay. So I will focus right now on a sort of canonical measurement that we are planning to do in the EIC, that is extraction of the G1 structure function from the double spin asymmetries. Okay, so we want to measure access the proton spin. We know that deep inelastic scattering gives us access or sensitivity to quarks. We also learned that in the unpolarized case, when we go to high Q squares and we are looking into the dependencies of the F2 structure function, for example, from X and Q square, we observe the scaling violation, and the scaling violation allows us indirectly access gluons. In case of polarized observables, we are looking into polarized cross-section. We cannot access proton spin without having a fixed polarization of our beam or our target. So we are accessing it through a differences of cross-section with different longitudinal spin orientation of the electron and the proton. So we will be smashing spin polarized beams and beams together, so electrons and protons. Why does it work? So you can think about it as the following. So the virtual photon is a boson, has spin 1, and it acts sort of as a spin filter. So when you look into the helicity conservation between spin 1 virtual photon with the spin oriented longitudinally to its movement and spin 1/2 quark, the conservation allows only in the interaction between the photons with a momentum that is opposite to the spin that is opposite to the spin of the quark. So the interaction will happen only when the photon has the spin opposite one more time to the 1/2 spin of the quark, which is extremely nice because we can just filter what we are probing. If we are smashing the proton with one spin orientation of the virtual photon, we are sort of probing or sensitive predominantly to one orientation of the quark spins, and we are doing it with the opposite. We are sensitive to the another orientation of the proton of the spin of the quarks. And of course, if we have an overall polarization of our system, so the polarization of the proton, which tell us, okay, protons are predominantly have spins predominantly oriented in one direction, we can check the correlation between what's happening inside, so what spin orientation our quarks have, to the overall orientation of the spin of the proton. So it's like a very general principle. I will show you now in like details how we are doing it and what are the exact formulas that allow us to extract the contribution to the overall spin. We talk about the longitudinal spin here, so aligned along the momentum of the proton. Okay, so what's really happening when we have an unpolarized DIS cross-section, and we presented it yesterday? We can write it down in the following form, with two structure functions, F1 and F2. And what is happening when we have both polarized lepton and nucleon, longitudinally polarized? So in the overall formula for the cross-section, we have an additional spin-dependent part that you can see here. LL just means that we have longitudinally polarized lepton and longitudinally polarized nucleon. And you see that this additional part is directly proportional to the G1 structure function, so the helicity structure function. And as we said also yesterday, in sort of leading order quark-parton model, we can directly interpret it as the sum over all flavors of quarks that we are probing, weighted by the charge square. And here what sits is the quark helicity distribution. And quark helicity distribution basically tells us to what extent quarks at the particular x, that carry particular x of the momentum, have spins aligned with the overall spin of the momentum of the proton. So one can say, okay, so we have to measure cross-sections with polarized electron and proton collisions. And we have access. Well, in principle, yes. In principle, we could measure cross-sections. It's just that experimentally, there is much simpler way. And cross-sections are generally quite challenging. So here you can see like a very basic standard formula for measuring any type of cross-section. In this case, d squared sigma over the x dq squared. So in two dimensions, the x and q squared. For our process, for any process, basically. So you can see, okay, we need a number of something. In our case, would be number of scattered electrons because we are measuring deep inelastic scattering. We have to normalize it to the integrated luminosity. So to know how many, what was the flag, what was the number of interactions we had. We have to take into account the bin size in which we are extracting our observable. There are also some more modern approaches to do really unbinned analysis. But in general, we need to account for the beam size. And, we are not measuring things in a vacuum. I mean, we do in some detectors, but we have to take into account our limitations of our experimental setup. So we have something what's called here acceptance and efficiency. So basically, you cannot cover all 4 pi of your phase space around the interaction point. There will be some gaps. There will be some non-sensitive parts of your detectors because you have to stack your cables, cooling, and several different things inside the detector that are not sensitive. So our acceptance won't be 100%. We will have some, for example, gaps in the detector. Detectors have also some type of efficiency, right? We cannot collect everything all the time. We reconstruct our events, our topology, energies, angles of the particles that escape our interaction point, and they are also not 100%. So you have to very precisely understand it, measure it, ideally through some redundancy if you're set up, or simulate it very properly. And very teeny tiny effects here can affect us significantly. On top of everything, in any cross-section measurement, you also in DIS, you need to also take into account the radiative effects and correct for them, as well as some sort of migrations between the bins. And what's up with these migrations? So generally, when you are measuring something in a experiment, like for example, energy and angle of scattered electron, right? In like a very simple scattering experiment. We never, can say in 100% that the energy, measured energy is, 5 GeV and the angle is 0.001 radian. We have to be, we have some experimental uncertainty. And what is happening is that when you are binning your observable in some fixed bin size, the detector effect can, for example, cause that the variable that should be fixed in one bin sort of migrates to another bin because of the detector uncertainties, the experimental uncertainties. This can be really magnified in the situations that you try to measure very steep observables, like a DIS cross-section, which drops very, fast with Q-square, for example. So you have to sort of unfold for it. There is the whole, set of methods, statistical methods that allow for it. And this unfolding happens, always. You will also have to, in principle, do it in your asymmetry analysis, but maybe, it can be a bit simple. Also, radiative corrections will be needed to be done in the asymmetry as well as in the cross-section measurement, but they will be much simpler. So, to kind of summarize whole story, cross-sections will be measured at EIC, but if we can avoid it, it's better to do it in the simpler way. Simply, it takes a lot to measure a cross-section. And just to give you an example, when we were talking about the F1 and F2 structure functions, we can alternatively also, write down the cross-section of the DIS into term of F2 and FL, so like a longitudinal structure function. And those measurements are very sensitive to gluons, to unpolarized gluon distribution, but they are, since they are cross-section measurement, they are by far dominated by the luminosity, total luminosity uncertainties. And, we've seen it for the Hera experiments. I think Tomat mentioned also yesterday that, that's why we want to really have very, very precise measurement of our luminosity. In case of asymmetries, this all disappears. We have some relative luminosity that we have to measure, but it's much, much easier. So bottom line is, if you can measure asymmetry, go for it. It will make your PhD take, 5 years, not 10 years in general. Not to say I'm a person who always was I measured some asymmetries in my life, but I was mostly measuring cross sections. It takes a lot. It gives you, lots of understanding of what's happening, especially with your detector. So, also go for it, go for both. But in our case, we will do it, much easier. So we will go to the asymmetries. So bottom line, it's simply a cleaner method. Lots of systematics also cancel. This is quite important because, if we measure some sort of asymmetries, as long as the effect that we are measuring is not spin dependent, because our asymmetries are sensitive to different spin orientations. So as long as those effects are not spin dependent, and better they will be. In the sense, if we have a hole in the detector, we hope that this hole in the detector will be independently if we have one electron orientation of the spin or another electron orientation of the spin. I don't know. It would be a very weird hole in the detector if this happened, it was spin dependent. But in general, those will cancel. And they don't require absolute luminosity extraction. Okay, so how do we do it experimentally? We are taking two orientation of the beams. We are basically measuring the, here I write cross section, but it will be a fluxes of a particular reaction, in this case, the just DIS, in the two situations. So when the spin of the electron and proton are anti-aligned, so like this, or like this, or where they are aligned. So in this direction or in this direction, we take all the possibilities and we swap between them in the experiment because we would like to minimize those spin-dependent uncertainties, right? So if we are swapping them quite frequently, whatever happens over time will kind of average if we are, if we are just swapping them during the measurement. So this asymmetry is of course, a asymmetry for the beam and proton. So the electron and proton. Sorry, I think sometimes a bit in the target regime, but in the sense in the electron and the proton asymmetries. But we want to access in the end the asymmetry between the photon and between the proton. So this is very easily related to the A1 asymmetry. And this is basically what we wanted to measure. So it's described here. So we have an asymmetry in the cross-section when the proton has been anti-aligned with the virtual photon, or the proton has been aligned with the virtual photon. And here we have a depolarization factor. So that is a kinematic factor. We can easily calculate it when we have access to Y, so the virtuality of our inelasticity of our interaction, and we can just directly link it to the double spin asymmetry. Okay, so what do we really measure? We said we don't want a number of observables and all those detectors, but we measure double spin asymmetry. This is ALL, sometimes written this way. I'm sorry, I changed the notation here. So we have number of scattered electrons with the particular electron-proton spin orientation. This has to be, in principle, normalized to the luminosity. We say we don't have to measure the total luminosity, and I will just talk a bit about this here. But in general, of course, if we have a bit longer duration during our run when the spins were anti-aligned, to when they were aligned, we have to account for it, because we just want asymmetry that is sheerly from the internal interactions with the proton, not the asymmetry coming from the fact that we are measuring with different times of the spin orientation. We have to also remember that beams won't be ideally polarized. It will be 100% polarization. By percent, I mean in average, how many spins in the bunch of particles is aligned with, for example, orientation longitudinal right to the motion of the particle. So there will be some factors coming from the beam polarization, electron polarization, And next week, Oleg will tell you more about how we really measure that polarization. This is actually really fun. And as I mentioned, we don't want to measure cross sections. So basically, when you just look into this formula, we can reduce it to just having here R, that it's nothing else as a spin-dependent relative luminosity. So basically what you need to know in the overall, time of running, what was the relative ratio of the luminosity when we had spins in the same direction and in the opposite direction. But this is much easier because this doesn't require the overall, some like a normalization. Okay, now we talk about the flavor separation on the International Donut Day. So we talk, that we can access spin of the proton through the DIS. We talk how to do it experimentally, like what do we measure? And right now one can ask, I think there was a question yesterday from you, if we can do it flavor separated, right? Can we access separately U and D quarks? Can we measure, strange quarks, etc., etc.? Okay. So actually we can. And one of the handles to do so is so-called semi-inclusive deep inelastic scattering with, for example, charged kaons or pions. So what we do in semi-inclusive deep inelastic scattering is that we are looking also into what is fragmenting, what our quark is fragmenting into. So what hadron is also produced from our struck quark. And this gives us, flavor dependent sensitivity to different quarks. If we add spin, it will be to the spin of different quarks through the fragmentation functions. So fragmentation functions are also those non-perturbative beasts that describe similarly to the Parton distribution functions. Parton distribution functions describe the probability of finding particular quark or particular flavor at the particular x momentum fraction. The fragmentation functions will describe us what is the probability that a particular quark of a particular flavor fragmented into a particular hadron, for example, pion or kaon. And this depends on Z, where Z is sort of the fraction of the energy of the final hadron sort of carries. So we get this extra sensitivity through CDs, and then formally what we measure, I will not go again step by step at all this process because the principles are the same. We again measure A1. We measure the asymmetries with different orientations of the beam and target, I want to say, so the electron and proton spin orientations. And, again, we can look into it at the leading order that gives us, sensitivity to the helicity distributions, but then flavor separated. And then, we can, in EIC, when we are looking into regions that are very low in X, so the regions of like gluons and C quarks, we can, get the sensitivity predominantly, for example, to anti-U quark by pi minus, that anti-D quark by pi plus, to delta S, so the strangeness contribution to the proton spin by chaos, etc., etc. So the measurement is very similar. We're just registering one more hadron. Okay, kinematics. So where we are and where do we want to go? Why we even bother, right? Let's describe it sort of systematically right now. This plot shows current world data on the polarized DIS experiments. It also includes actually Greek data. Yes. On the determination of the proton spin. On the y-axis, we have x, momentum fraction. Here we have a resolution power u squared. So you can see several different regions. You see in the regions that are, as I told you, right, 10 to minus 2, maybe 10 to minus 3 from RIC. So these are proton-proton collisions. These are measurements at W boson scale. So this is also from RIC. This gives us access to the C, so anti-U, anti-D. And here you can see, all the data points that originated from the DIS measurements. So, spanning from very low Q squares and X, like for example, measured in JLab, into sort of intermediate region. And this is a log scale. So, all those plots in like yellow report on EIC are always plotted on the log scale. So people sometimes like, oh, we know a lot. Well, no, we don't. We just see it in the log scale. So, and then of course, this region here, all region here is significantly dominated by gluons. And you can see also what's up with the EIC, right? All those lines are showing what will be our kinematic coverage for the future measurements, depending on the different beam energies. So you can see that things are really going all over the phase space. I also wanted to show you where we currently are with all the CD's measurement of the G1 structure function. So yesterday we were discussing F2, and you've seen this, scaling violation and measurements spanning from very high to extremely low X from Hera with the huge Q-square range. And here we are quite limited, honestly speaking. We still have quite good handle of the spin of quarks, but like almost zero scaling violation. Like everything is flat as bikepaths in Illinois. So everything is really, really dominated by quarks. And this region, one more time, that we currently have is corresponding to this corner, and we'll be spanning all over here. Also, pay attention that all the points that are in the region outside this pink area are from proton-proton scattering, right? So these are really, they are good observables, but quite complicated with respect to a simple electron probe. Okay, so now we will talk about the experimental requirements, and I think we should do some brainstorming because I talk quite a lot. Okay, so we talk more or less about what we have to measure, like in the very simple terms, to have our asymmetry. So to measure deep inelastic scattering and really access the gluon spin, let's take DIS as a first example. What would you want to detect in your detector in the very first place? For the DIS, for the deep inelastic scattering?
The electron.
The electron, okay. So how simple as that, right? The simplest possible measurement, fine. We need this electron, of course, with a different spin orientations. How do we measure electron? What do we need from this detector, from this electron? We say we measure electron. What do we want to measure for this electron?
Momentum.
Momentum, okay. Energy momentum, right? We need angle and energy, or momentum and energy, to have X and Q squared. This gives us our kinematic variables. Fantastic. So now, how do we measure momentum and energy of the electron in any detector? There are several ways. Calorimeter, good. So we have one way to measure in principle angle and energy, right? Something else. What else? What else? Electrons are charged, so where we can measure electron. Bending of track. Very good, right? So we have also a tracker. So we have a momentum from the tracker or momentum from the from the calorimeter. Very good. So, in principle, this would be like, okay, we are done. We are good. Of course, in any measurement, apart from a signal reaction, we have also background reaction. I don't know if anyone could, possibly think about what might be a background for our single electron. You said something design, in the sense we have something that, for example, is a state that decays to 2 electrons. Okay, one, for example. You said what? Muon, for example. Okay, so muon, we could say we have charged particle that also interacts electromagnetically. Okay, what else? Who says photon, right? Someone said photon. Okay, what else could be? We'll all. You said pi zero.
That one the case, right? So it wouldn't be coming.
Yeah, but the same as Jay said, these are all good examples. We'll just say how we're then later removing all of those backgrounds. There's another background that it's particularly nasty and maybe didn't come yet to your thinking. It will be. Say again. Low energy hadrons. Low energy hadrons. This is good. This is very good, and I will show you in a second why. So let's go and dissect all of those. So we said J psi. This is a good example. I mean, J psi is a particle that decays to 2 electrons, right? So we want to make sure that we will detect 2 electrons, try to, detect their invariant mass and see if it peaks, for example, at the J psi. So this will be one contribution. Someone had said photon. Photon is easy to separate because it's not charged, so it doesn't leave a sign in a tracker. So this background, okay, we got rid of it. Then we said muon. Muon will give us certainly a track, but muons will not shower in the calorimeter. Muon mostly act like a minimum ionizing particle. I see the question.
Maybe a decay of electroweak boson?
We could have a decay of electroweak boson. Sure, right? Any sort of decay particles can give us background, but we have to also think about the cross sections of we want to measure, right? So if it's very low into respect to what we have, it's really sub% process, of course, we won't bother.
Yeah.
But some of this will require correction. So this is not, in some regions of kinematics, it can matter. Absolutely, absolutely. If it's just an electron, single electron, right? Absolutely. Someone said low energy hadrons, and these are particularly nasty, and I will show you why in a second. Did I cover everything? Pi zeros. Yeah, pi zero will, you don't have a track if it's pi zero because it's not charged and it decays to 2 photons. So basically, unless we had like extremely messy tracker not working, which we won't have, of course. But if it happened, then, there might be a possibility. This was all good, very good. Okay, so from the point of view of the facility, we, had all our measurement pen and paper on the, slide saying we have to measure, different polarizations, etc. So of course, our machine has to deliver to it. So EIC will be, actually, as of now, the only collider project anticipated in the near term, which also, gives amazing opportunities for every of you or everyone who is interested in, collider/accelerator physics too. Basically, to just think about how we, accelerate particles with extremely high luminosities and those, very complicated spin orientations. This is not trivial. It will deliver very high luminosities, much higher to this what we've seen in HERA, which is also needed because usually, when you have a polarized beam, some luminosity can suffer a bit. So that's why we also need all of those to be really going intact. And it will allow us to collide spin-controlled beams. So thanks to very sophisticated set of steering magnets in our machine, that for sure, I know, I think Christopher Montag is giving talk, I think next week, right, about accelerator physics and how everything comes together. This is really extremely interesting. We will be able, to steer the spins of the protons and electrons inside the ring, which is, the spin dynamics of the beam is extremely complicated. You can think about it that basically spins are rotating in the extremely high resolutions in the plane of the accelerator. And any sort of small disagreements and small effects of the magnetic field can completely ruin, our understanding when the spin is at a particular moment in the accelerator. And if you really want to control it and make sure that at the particular collision point, like for example, in our detector at 6 p.m. or maybe a future detector at 8 a.m., the spins are exactly oriented as they should be to collide, either longitudinally as in our case or in a transverse way. So it is non-trivial. And moreover, to go to all the heavier nuclei physics, the EIC will allow us to go to the higher species of nuclei from deuterium, basically, possibly to uranium. Okay, so now detector. Thomas discussed a lot of, subsystems yesterday and showed, what we'll be measuring when, but right now, since we have one case study, I think we will be very nicely able to see what is going on. So this is like a cartoonish example of a peak of our future detector at 6 p.m. of the ring of the Future Electron-Ion Collider. And here you can see what region of our phase pairs, of our kinematics, we can reach with scattered electrons. So when we go with this purple line of a Q square, you can see directly what Q squares are we accessing, so what resolution powers, depending on the scattered electron. So in the backward region, when we really have to have extremely, good resolutions, and where majority of our electrons will go from the, scattered beam, you will have low to mid Q square. And then the further you go, you really are reaching high Q squares. The resolution of the kinematic variables determined from electrons in this region will be extremely poor. So then we have to switch to hadrons. So we have a full system. We need, just as we say, for example, the energy and the angle of the scattered electron, or Q square and Y, or Q square and X, to describe our process. So we can also measure the final hadronic state. So instead of the single electron, we measure everything, what this jet of particles that was produced in the interaction apart from electron. And this also gives us, sensitivity to X. I mean, we can also get X, of course, just from the electron measurement. And you can see with the hadrons, where we go, the X will be changing. So the backward region is low X, low Q square. So this is like a saturation region. Here, we have a medium X, medium to low X in the central region with quite high Q square. So extremely good resolutions. And, high X values will be in a forward direction.
Out of curiosity,
Yeah.
is there a concept of multiplicity of how, besides because Thomas said something about it's hard to think of, because the electron is a point source, of where it crosses, whether or not you can determine how head-on or central versus side of the nuclei it
Oh, like in the heavy ion collisions, like the planes of the scattering.
Is it more like you get it from whatever is going that way, from the remnants, or I don't know what Hera did or in what it plans to do?
Well, you will have a very forward and very backward detectors too, so you will be able, to measure those.
So I guess
You will be able to measure also, somehow also a hadronic plane,
Yeah.
because in the similar way to what you measure in any PA collisions, for
Yeah.
example. Think about it this way, right?
Yeah,
Because you will have a number of particles that are being produced. Of course, electron, in this sense, like if don't want to directly compare it, electron is a point-like particle, right? So we don't have, in this sense, centrality, right, of the interactions here. But this is a very good question. So think about it as something point-like, smashing with your usual, very high density hadronic state of nucleus or a proton. What you immediately can see from this picture is the asymmetry in the beams reflects directly into asymmetry of the detector, right? This is very different than in any other PP collider. You see that where hadron goes and where we really heavily rely on the hadronic final state to extract our kinematics, we have huge hadronic calorimeters and very thick electromagnetic hadronic calorimeters. In the region when predominantly electron will go, and we will rely on the scattered electron to extract our kinematics, we have extremely precise electromagnetic calorimeters, and Barrel has to do everything. Okay, this is the picture of EPIC detector that you've seen already yesterday. I think it's just absolutely stunning, and I will tell you a bit more about the subsystem important for the polarized DIS. But of course, I will not go into detail into everything, but wanted just to tell you that we will have 25 different subsystems that include also polarimetry, because we have to measure the degree of our polarization. And there's really many words first in EPIC regarding the technology that we are using to really achieve our physics goals. So this is a bit of the laundry list of what requirements do we need. And I really love that we started brainstorming what we need where. But basically, for the DIS, for deep inelastic scattering polarized, we need to measure the scattered electron. We need to do it very precisely in the backward part of our calorimeter. So we need very good calorimetry in this direction. In the central region, it can be more moderate. It's also significantly better supported by a tracker in the central place. So you mentioned that we can also measure it from tracking. So there are those two complementary, measurements that we can do. That's why the requirements are a bit lower. The nastiest background for any sort of, DIS measurement, not fully exclusive, but with single electron, are by far single pions. Single pions that are low energy, negatively charged pions that originate from the final hadronic state, that originate from the struck quark, can give very, very similar pattern into our detector. They are charged, they will give us a track. They will have a some energy deposit into electromagnetic calorimeter. Normally, when you think about electromagnetic calorimeters, you think about the photons and the electrons, and you are saying, okay, pions don't shower in electromagnetic calorimeter, then go further. And then, the only thing we check, we have electron and photon. But if the pions have very low energy, there is a non-negligible probability that this will happen. And one could say again, well, if it's a very teeny tiny fraction, no one cares. Well, if you have a huge cross sections of producing low energy pions from your semi-inclusive deep inelastic scattering, and in your measurement, you're just relying on this one single electron to measure your X and Q square, you can be screwed basically. So you have to make sure that you have a good electron pion separation up to the order 10⁴. And these are by far, the strangest conditions in comparison to any high energy physics requirements. And I remember once I was preparing a white paper together with my colleagues from HEP about requirements for the, some detectors. We're talking about the CMOS sensors for particle identification in calorimeters. And I was writing some sentence in the draft and I wrote our calorimeter is very important for detecting scattered electrons. And there was a comment by someone, on the site saying, oh yeah, but every calorimeter is important for registering scattered electron. What's super, important about it? Let's remove it. And, no, because this electron is the electron. And if we miss it and we don't have this one, but we measured some random pion, we completely don't understand the part of our kinematics. So yes, this is extremely important. If we talk about the CDs, when you think CDs, you should think, yes, please.
Electron pion separation up to 10⁴.
Yes. What does it mean?
10⁴ what?
Okay, yeah. So it's a suppression factor. What does it mean is that if you have a sample of pions with respect to sample of electrons, you have to add 95% electron efficiency. So you're saying I'm not rejecting more than 5% of my electron sample. I suppress my pions 10⁴ times. It's a lot. Like usually, like any typical calorimeter will have like a factor 10 to 2, maybe 10 to 3 max. So it is, it requires either extremely good energy resolutions or tricks. And I will show you the one trick. For any cities measurement, as I mentioned, you think cities, you think particle identification, because we need the hadron on top of our electron that, you know, is produced in this reaction, and we have to identify what type of hadron it was to know to what type flavor of quark we are predominantly sensitive. And when we talk about the any measurement related to the orbital angular momentum, for the GPD measurements, etc., for the spatial imaging of the proton, you have to think high luminosities and forward detectors on top of everything, because we have to catch everything that is escaping our reaction. I'm almost done. Example of the calorimetry. This was, I think, the exact picture that Thomas showed yesterday. And I just basically took the requirements that we had for the DIS and put it on all of those. So superior electromagnetic energy in the backward region, bam, lead tungstate calorimeter. Separation of electron pions up to 10 to -4 and reasonable energy resolution. Imaging calorimeter from scintillating fiber in lead, supported by the silicon sensors. High granularity calorimeter to detect jets, and very good hadronic energy resolution. Our lead tungstate, not lead tungstate, our scintillating fiber tungsten powder calorimeter, and the highly segmented hadronic calorimeter. So we immediately see how things are being, you know, complemented to each other. And then you can also see that in generally in the central region, our energy and momentum extraction can be done predominantly by our system of trackers. So here is one way. So I had to show it to you because this is my baby. This is the detector I'm building at Argonne. It will be a 40-ton baby with a, I don't know, you aim for what you can in your life, right? So this lead sandwich, so a sampling calorimeter that in the central region requires also extremely high electron pion separation. But you know, if you would like to build it out of lead tungstate crystals, it will be just prohibitively expensive. We cannot do it. So what we are doing, we are using a sampling calorimeter that is sandwiched with the CMOS maps, so monolithic silicon sensors called Astropics that are produced from the Amigo X mission in NASA to see how the showers develop where particles hit it. So it's just one of the examples how, apart from the total energy measured in our calorimeter, we are able to say if it was electron or pion. And you see in total, they are not that different, but they are a bit different. So electrons will shower early in the calorimeter with regular patterns, and pions will usually start showering a bit later, and the patterns will be very wide and irregular. So if you can have sort of 3D image of your shower in your calorimeter with a good precision, event by event, on event by event base, you know, based on machine learning techniques later, you are able to significantly suppress the pion background to the electrons. So that's why we are building it. Okay, particle identification was covered yesterday. Basically, I just wanted to show you that for any like CDS measurements, you know, you will have your pions and kaons that you want to measure in the wide range of momentum that had to be covered by a really wide range of different experimental methods for particle identification in different ranges. So here is how we are covered. This is just example from a PEFIA electron proton simulation showing where basically kaons and pions go. And that's why we have to now cover it in such an extensive way along the whole region of the central detector. Okay, and last but not least, I promise you the impact part. So here is where we were in the beginning of the word data sort of status. So taking into account, for example, G1 measurement with all those considerations of how well we will be able to measure in our detector, how much luminosity we will have, how much polarization we will have, what will be the coverage of our detector, how long we will be running the EIC, etc., etc. All those considerations we can estimate, putting it into sort of constraints on the global analysis of the extraction, that using the 45 GeV square root S data, most probably, I mean, don't look at the central point, it's just basically the error. We will be able to shrink the uncertainty to more or less this blob in the center, and then pushing into all energies. We aim, or EIC basically aim to shrink it, depending of the angular momentum axis or the deep gluons axis 10 or 22 times. So this is our aim. You can also present it as a function of X. So again, the helicity distributions, how they are running with X, and you can see that, this big blob with the region of 10 to -3, we hope to be shrink, significantly down. There will be also some impact on the delta, on the quark contribution to the gluon spin, especially in the low X region. And here you can see also impact on the flavor separated distribution from quarks, especially from the C, right? Because the valence quark region is basically well described, but looking really into C, where we can get very good access from the low X region, we will have a significant impact also there. So last but not least, I just want to say that EIC is really a candy store of physics opportunities, and you are extremely lucky that you are here at this stage of your career. I'm also incredibly lucky because we can build detectors, we can shape the future of the EIC regarding to what we can measure there. We can be involved at this stage already in the project that will start running within our lifetime. Not many communities can say it, especially in the particle and nuclear physics. So I think it's extremely rewarding to work on it. Today, I focused only on a few case studies, mostly for the proton spin. I don't want to make impression that EIC will be only about the spin. There's tons of examples, and please, when people are around here, ask them, what are you the most excited about in the EIC? Because everyone has their favorite candy in the store, and there's so many, opportunities in 3D momentum space imaging, in spatial imaging, in precision studies of nuclear effects and saturation. There's really and beyond, there's really a lot we can choose from, and it's also your time to shape it, right? To do simulations, to do feasibility studies, to understand what we will be able to access, to brainstorm solutions of both on the detector side, experimental side, and on the theoretical side. So the summary, I would just say that EIC, I strongly believe that EIC will really profoundly impact the most fundamental understanding of the inner structure of matter that builds us all. We'll be able to access it through large kinematic coverage, polarization, access to protons as well as heavier nuclei, and high luminosities. And last but not least, I also wanted to advertise our podcast, which is called Strong Interactions, and it tells about the story straight from the heart of matter. If you want to listen more to my Polish accent or German accent of my co-host, I invite you. And we talk about many things. We will measure at EIC, from the longitudinal spin structure to TMDs, lattice QCD, etc. And it's still evolving, and the new episodes are coming. So thank you so much.
Maria, for your engaging lecturers. So please have questions or comments. All right.
In the slide 21, you said that during the fragmentation functions to get to the flower separation, it's not the uncertainty in the low X regime a problem.
Yeah, it would be, of course. Of course. That's why we need complementary, to some extent, measurements and understanding of what we can do really in this region. Yes, this is one of the certain limitations. Yes, any low X input that we will need to any of those measurements will be challenging.
Because
Right?
for you, it's an input, no? It's not something that you're trying to
I
measure.
mean, you can also measure fragmentation functions, of course, so it will go hand in hand, right? But to measure fragmentation functions, you need to know, I mean, if these are just unpolarized fragmentation functions, that's fine, right? If you are talking about something more exotic, but then, you are not, usually you will not have more exotic fragmentation functions if you want to access just simple longitudinal spin structure. If you go to something more sophisticated, like, we talk about the transverse momentum, etc., then of course it will be also the first measurements and we will focus on those fragmentation functions too, right? So basically, to some extent, it will be going hand in hand. For the unpolarized fragmentation functions, we have access already from the previous measurements, right? So we know that in the low X regime of, maybe, LHC, we have access to those. Ideally, of course, we'll have access with the very pure measurement like E plus, E minus, right? This is sort of course, the best, right? Because then you can very precisely extract your FFs. But FFs are as important as any other input in what we are doing. But it will go hand in hand. It's not by far the most limiting, I would say, in any city's measurements, but in general, yes, we have to be careful about this.
Is it possible in principle to measure the helicity of final state particles?
Helicity of the final state particles. We will have to find a way to do so, right? It would have to be in principle, yes, it would. What I mean by this is we have to find the observable that allows us to do so, right? So if you have a lambda polarization in the final state, for example, so they are already, developed sort of frameworks that we can really measure it and think about it, right? For the EI, so there's a class of measurement that you can do, but do you think about something particular? Just in general?
Like an exclusive process, the proton after it scatters. That's
I mean, usually the interaction sort of destroys the overall polarization. So, on the event by event basis, this is not feasible. You would have to do it through, as I told you, like a class of measurements, like for example, with lambda. Yeah. Yes.
I didn't quite understand why relative luminosity is easier to obtain than total luminosity.
Yeah, because relative luminosity, you can, you basically what you are sensitive to, you don't have to measure it absolutely in the sense you don't have to know the cross-section and number of events that, for example, produce a Bremsstrahlung process based on which we will be extracting our luminosity in the particular chunk of your data. What you have to do is just say, I have, let's say, minutes, right? 2 minutes of my data with this kind of polarization and 2 minutes of my data with another polarization. So what I need is just a relative number. I don't have to care about the absolute normalization of it. So basically, I just say, 500 events versus 600 events. That's it. I don't have to take care about the all, acceptance, efficiencies issues that allow me to get the absolute normalization from a known process, right? So it will be, and also, we have to remember that I'm talking about it like it's impossible. I mean, we'll be able to measure luminosity to a very good precision, but simply, we talk about 10 to minus 2 precision versus 10 to minus 4 in the relative. So simply by the methodology, we are able to, push it even lower in the uncertainty. Yeah. Yes.
Could you explain? I don't understand. Because in the first plot, you have the next 1 point is 10 to minus 3 and q squared close to 1 or 2.
This is q squared. This is q squared.
Yeah. And the last point up. X is 10 to minus 3. But in the right plot, you don't have this point. So I don't understand.
Yeah. Okay. These are not exactly the same points because, okay, so here we have Hermes, okay, so let's look into it. So you are saying that you have, well, I mean, okay, so 0. Okay, so this up region is 0.003, right? So it is roughly here, right? No, it's 3 10 to minus 3, right? So 1 2 3. So it's roughly here. So these are those ones.
Yeah.
Right?
Yeah.
Yeah, again, this is log scale. I know it's, we are not used to reading log scales. So like when I look at this plot, I also say, oh, where is this? Yeah, but this is here. So these are those corners basically here, right? That you were seeing. At very low, this is low Q square. And like a corner of the measurements over here. Yeah. Yes.
Is it planned for the EIC to measure process like double DVCS? Because as you know, we cannot extract the same information from
Yes.
DVCS for the GPDs
Yes.
that's from
So,
DVCS.
I mean, sort of detector-wise and possibilities-wise, it will be certainly an interesting option. We would say that probably yes. We have to be, of course, very honest with this, how much luminosity we have. So this won't be day one measurement. We have to think about it as, when the accelerator is starting running and when we are ramping up the luminosity. This is very luminosity hungry process. We need lots of beam to be able to access those extremely low cross sections, right? Because they are exclusive. So it won't be day one measurement. It will be, shifted a bit in time when we have better understanding of our accelerator and when we will have more and more luminosity available. On top of it, double DVCS, usually it's very, not to confuse it, it's very nice to measure with the decay of muons, right? So that in the final state we have muon. And those capabilities, we have to some extent in our detector. So, it's not fully optimized detector for muons. We can do a lot. So you can think about it as, further in the time because of the luminosity, and experimentally quite challenging if you want to get, double muons. So this is, maybe also possible upgrade, etc. For sure, this will be one of the things that people will be interested. It's a, staple measurement for any, DVCS processes and GPDs. Absolutely. So I think so. Just not, first day after we switch on the accelerator.
Thank you.
I have one question. So on slide 17 or 18, you talk about the luminosities. Yeah, the next one, 18. So I was wondering why the uncertainties in the luminosity measurements cancel exactly. Because I do understand they use the same methods to measure the luminosity for both beams, but I don't get how it cancels exactly.
I mean, they don't, they are still here, right? If they will cancel, if the luminosity will cancel exactly, we will not have this R here.
So the uncertainty of the luminosity.
The uncertainty will be, if, okay, why, okay, it wouldn't it won't fully disappear, but basically to the first order, you say that if you would have any uncertainty that it's heavily dependent on your spin orientation, that it will propagate into the asymmetry measurement, right? So if I would say that if the spin of my proton was in the one direction versus another, and for example, my detector that I'm measuring my luminosity behave differently when I had one orientation of the spin versus the other orientation of the spin, then this first order uncertainties will not cancel. So when we are measuring asymmetries, what we are one more time searching for is any spin dependent effects or uncertainties that will be there. So in principle, if I measure a luminosity of the flux of particles with one orientation and my process is not, sensitive to the spin, and I have detector that is all the time the same. I mean, it can change with time and we have to, calibrate out or remove this time dependence in general. But if this doesn't, the number of particles doesn't depend on the orientation, or we know it, with the extremely good to the extremely good extent, we are the first order effects, we are not sensitive to it. So its measurement as any other measurement of the cross section, you can think about it. Measuring luminosity is like measuring the cross section. You just have a known cross section of the process, and you measure number of particles from which you extract the number of particle, right? In the cross section, you measure number of particle and luminosity. So you have so it's kind of similar.
Thanks. We have lectures by Oleg guys who's going to talk about polarization. Excellent. Let's thank.
There's some details about schedule. We have a relaxed schedule today, so let's go ahead and take a half an hour. And let's see, I have for New York, I printed out some flyers. I don't have enough for everyone, but if you want to look that over, have any questions, and if you want to do laundry over the weekend, there are Tide Pods here, and I have more. So